It's my pleasure to introduce Professor Gaël Richard, who's now professor at Telecom Paris, now in Palaiseau, a little bit south of Paris. I had the pleasure to spend a few months with Gaël in the spring, and we had a great time. It's a really nice campus. I encourage everybody to visit. So Gaël is also the co-scientific director of Paris, I guess, and it's an AI interdisciplinary center with focus on application of AI to business and society. Gaël has done a lot of work over the years on sound and music, very influential work in NMF. And he's going to talk to us today about deep hybrid learning and its application to unsupervised singing voice separation.
Recording in progress.
Thank you very much, Jonathan. So I'm very glad to be here, to be in New York and it's SANE workshop. It's a very nice workshop. So yes, I'm going to present some work. Make a brief overview about what I call deep hybrid learning, and spend quite some time in an application of this principle for unsupervised singing voice separation. Okay, so this will be the content of my presentation, a bit of context and motivation, then a few examples of how to go towards hybrid deep learning with some examples in other domains and some examples in hybrid deep learning in audio, and then a specific focus, as I mentioned, in unsupervised music source separation. And then if we have time, a bit of discussion and conclusion. Okay, so context and motivation. If we look at the current trend, or at least one of the major trends, is that we go more and more towards pure data-driven deep learning approaches. And also the main reason for that is because we can obtain high performances. And it works well, and so then let's do it. But of course, following this path, I would say that there are some main important limitations. And I think the major limitation is that the knowledge is only learned from data. And we will see that this induces some problem. And also, another problem is that it's complexity. Because the knowledge is learned only from data, we need to build big models, over-parameterized models with billions and even more numbers of parameters. And basically, the consequence is that we work in an overconsumption regime, both in the need of data, but also, of course, in the need of parameters for the models. And also another consequence, in many cases, the models that we build, because we have so many parameters, and that the knowledge is learned only from data, the model is, to a large extent, non-interpretable and non-controllable. So this is basically what is at the core of an ERC grant that I obtained recently. It's to build controllable and frugal machine listening models based on expressive generative modeling. And in fact, behind this is or my approach, I will say, that is to build hybrid deep learning models by integrating all prior knowledge about the nature of the processed data in the model. So still using data-driven models, but integrating prior knowledge through models. So this is not a new idea. It's done in other fields since quite a while, and especially in domains where they have huge and very, complex models about the physical natures of a phenomenon. For example, for predicting the temperature exchange of a lake, they have big models, physical models based on physical rules. And if they are using only data, then they will lose all this knowledge about these big physical models. So, and basically it gives an idea of what is called the physics-guided neural networks, which is it's a way of doing hybrid deep learning. It's mixing physics-based models which have very few use of data, but use of theory and physics theory, and use of black boxed deep neural networks, which use a lot of data, but maybe less knowledge about scientific theory. And there are also other domains, other aspects of this hybrid deep learning in image processing, in digital communication, and as I will see also in audio, with a number of different approach and semantics on how to describe what is a hybrid deep learning model. So you have a drawing here from one of the paper, an overview paper of the field, which separated this hybrid deep learning under the word model-based deep learning, separating what is DNA-aided inference and what is model-aided networks, which depends on where the model that you use is within the deep learning architecture. Okay, so then just to go a little bit more into details in this concept, you have a path which is the domain knowledge. So more you go on the right, more prior information or prior knowledge you use with your model. And more you go on the left, more data you use and less prior knowledge about your model, about the data you use. So if you're purely on the left, you have the typical pure data-driven models. You just input data and then you output other data or labels of whatever your problem is. And further, you go on the right, you input more domain knowledge, and you can input this domain knowledge at different places of the neural network. You can input domain knowledge at the input of your model. You can put domain knowledge within the neural network, or you can input domain knowledge at the output of the network, where you will use the neural network to predict parameters of your model. So this is just an illustration why it could be, and of course there are many different ways to incorporate this knowledge from the models within the deep neural network. So why hybrid deep learning is interesting for audio? I think it's interesting because we have many a priori knowledge about what is audio. And so many a priori knowledge about the sources, for example, that you are going to analyze. In fact, we have also a long history, as in physics, with audio signal models. We have audio perception models. We can, in fact, describe to some extent how we hear the different sounds. We can extract knowledge from psychoacoustics. We can also extract knowledge, and we have models also for that, for audio sound production. So this is especially true for speech. We know exactly the instruments that produce a speech, vocal folds, vocal tract. We can also include models of how the sound propagates in an environment, in a room, in an environment. We know what is reverberation. We know a little bit of what is room acoustics. And also we can use audio signals models that we have some prior knowledge about audio. If it's music or if it's speech, we know that it can be a sum of harmonic signals. It can be noise, and we know the shape of the noise it could be. We can represent the sound with time frequency representation, with decomposition models. And I will give a few examples of that. And also what is interesting in audio is that it requires some specific architectures of a deep neural network, which in fact, the fact that we know what is audio, we know what type of characteristic we can use. And I'm very happy that Arshad Nagrani mentioned that. In fact, an image, a spectrogram, an image of sound is not exactly the same as an image, because in fact, in an image, you have this sense of locality. An object is locally placed in an image, and the y-axis and the x-axis mean the same thing, which of course in audio, it's not the case. It's a specific case of image. You have a specific structure. We can see the sum of harmonics in the spectrogram, and we can see also that, and we know that the y-axis is different from the x-axis, where the y-axis represents the frequency, and the x-axis represents the variation of this energy in frequency with time. Okay, so now we are going to move, just to explain a little bit more the concept, we are going to move from the hybrid deep learning models explained in physics-guided neural networks to the hybrid deep learning for audio. We are going to replace the physics-based model by one of the models which characterize the prior knowledge we have about the audio sources. So either a perceptual model, a signal model, a physics-based model of sound production, or room acoustics, or even if the sound is music, we can use musicological models. What is a theory of a melody? What is a theory of the succession of chords? And so on and so on. And then the expectation is that the hybrid deep learning model will gain from the two words the capacity of the small models to characterize the prior knowledge and the capacity of the deep neural networks to learn from data. So just to give you an example, it's a simple example of mixing prior knowledge with a deep neural network. So you should maybe of you should know what is non-negative matrix factorization. It's a decomposition method which aims at interpreting a spectrogram, so the image you have in the upper right corner, as a sum of basic elements that can be atoms or elements of a dictionary. So basically here the spectrogram represents first a note, a musical note that is played, then a second musical note that is played, and then the sum of the two notes on the right. And you can express this spectrogram by only two instantaneous Fourier magnitude of a signal, which are the atoms, which are described in blue and red on the table on the right. So this is a dictionary. And the H matrix will characterize when each of these elements is activated with time. So the blue note, the blue spectrum, which is the first note, is activated at the beginning and then at the middle. And the red note is activated in the middle of the sound and then at the end of the sound. So this is a way to describe the content of the signals in a more semantic way than just the input spectrogram. And we did some work with that by using this representation as a feature extraction mechanism. So basically, the H matrix was representing the features that are of interest. It's the activation of the dictionary element. And we could show that if we were using this type of feature learning with matrix factorization, that it can lead to the same performance with a much shallower network because we have characterized the prior knowledge with this signal decomposition method, which takes into account what is typical characteristic of the audio signals. And the consequence of this is that we could have a smaller network to do the same task for audio scene recognition. Basically, audio scene recognition is the task of recognizing in which scene the recording has been recorded. Another example of deep hybrid learning is to take an algorithm which is iterative. So it could be, for example, again, this non-negative matrix factorization, because one way of solving this problem is to minimizing a distance between the reconstructed signal and by the sum of elements. And to solve this, one of the solutions is to have an iterative algorithm by iterating by an optimization, an update on the H matrix and an update on the W matrix, which is a dictionary. And this is an iterative algorithm. You can translate this iterative algorithm by expressing at least one of the iterations as a layer of a deep neural network. So then you can learn all this process with data, but it's constrained by the fact that it obeys, I would say, the principle of non-negative matrix factorization. Of course, there is one limitation in this type of algorithm, is that the number of layers is directly linked to the number of iteration, and of course, this may be a limitation for the algorithm. You have other examples of that. Is, for example, for doing, which is a bit similar to the previous example, is to do phase retrieval, where you only have the Fourier magnitude of a signal, and you would like to recover its phase spectrum to be able to rebuild the natural signal. So again, there are some algorithms to do that, which are also iterative algorithms, such as the Griffin and Lim algorithm. And again, for this type of approach, you can make each iteration within a deep neural network. So here, the concept is slightly different. So you have the example of in the drawing there. You have the two steps of the iterative algorithm of Griffin and Lim, of two projections, PA and PC. And basically, the deep neural network, what it will do, it will just denoise this step for each iteration. So the data will help to make this iteration, the classic iteration of graphing in Lim, less noisy, so then more efficient. And so then it will converge to a better solution with because you can take into account the power of data to denoise each step of this alternative algorithm. So then, again, it's kind of a hybridation between taking knowledge from the signal processing and taking knowledge from the data within a deep neural network architecture. And another example that I would like to present, and because I'm going to use this example in the following of the presentation, is this model called DDSP, for differentiable digital signal processing. And basically here, the data and the model will be used to learn parameters of a simple synthesizer. So the synthesizer basically will generate sinusoids at a fundamental frequency with a given amplitude, and will add noise, filtered noise, and then add reverberation. And all these parameters will be learned using data with an encoder and a decoder. And the optimization of this full synthesizer, I will say, is just to compare the incoming audio and the synthesized audio and use a multi-scale spectrogram loss to optimize the difference between the two spectrograms at different resolutions. And this model is quite efficient to in fact, exploit data to generate the synthesizer. So then I'm going to use also this model in the presentation when to embed this type of models within a complete unsupervised source separation paradigm. So now let's dive in the problem of source separation. And keeping this idea of using the concept of hybrid deep learning. So when you do music source separation, basically you have polyphonic music, which enters your big network. You have a music database, and in the music database you have a pairwise association between mixture of polyphonic music and the individual sources which compose the mixture. And then with your neural network, only based from data, you are going to learn how to separate from the polyphonic music the different sources which compose the mixture. So of course, the main limitation that we have with it works very nicely. We have excellent systems that can do that, very efficient. But there are some main limitations, and similar to what I've discussed in the beginning, it's difficult to obtain aligned data, which means to obtain data where you have the mixtures and the separated sources. The knowledge is learned here only from data. You do not suppose at any point of time what type of source do you have and what are the typical knowledge of an audio source. So then you have complex model and you operate in overconsumption regime, and it's also quite non-interpretable and non-controllable. So what is the idea here is that says that for the sources that we know, for example, singing voice, we know that they can obey a classic source filter model, which has been introduced for speech a long time ago. And basically, it says that the speech signal, or the singing voice signal, is a source signal produced in the larynx, at the vocal folds, which is a periodic signals, then this periodic signals is filtered by the throat, and by changing the throat shape, we can produce different vowels. It's a very simple model, and of course in the spectral domain, then you multiply the spectrum of the source by the spectrum, the frequency response of the filter, which obtains and then gives the frequency representation of the speech. Okay, so then the idea will be now, instead of directly predicting the individual sources, we are going to embed a model within the network, which will be a differentiable generative audio model, where we have a few parameters to control these generative audio models. So basically here, the singing voice, which is one of the source, will be represented, for example, by a source filter model that we know that it's controllable by a few parameters, and it's very characteristic of the sound that can be produced by such a model. So then here we are in a new paradigm. The model is at the core of the neural network. The source separation is not anymore a source separation paradigm, but it's a source separation by synthesis. So since you synthesize a source, you can expect to have absolutely no interference from the other sources. And the learning is done only from the polyphonic recordings. There are no more needs to have the individual sources to learn the full model. And since also you have a signal model, the source production models inside the model, then you have novel sound transformation capabilities because you have a F0, you have the fundamental frequency, you have the filter, you can change the phonemes, you can change the melody, and so on. So you have controllability, which is another gain that you have by using a model inside your deep learning model. Okay, so then what is the application I'm going to show here? Is that I simplify a bit the problem. So we are going to work with choir singing. So then we know we have only one source filter model because it's all the sources are the same. So we know the physical model that produces the sound for all the sources. And it's only one model, which is a source filter model of speech production. So the highlights is the same as before. It's completely unsupervised. You need only the choir mixtures, but not the individual recordings, which is particularly good for choir singing because usually choir singing, everyone sing together, not one after the other. But also one of the things which makes the problem a little bit harder than the previous problem is that all the sources are the same. So of course they are homogeneous. They will sing, in most cases, in harmonic relation, if they are in tune. And all the sources have the similar acoustic properties, which makes the problem a bit more difficult if it were different sources. But we have this prior knowledge, which is characteristic of each of the sources. Okay, so this is exactly how it works in general. So you have the mixtures coming in. Since we, at first, it was not working when we embed everything and we try to do end-to-end architectures, we had to estimate the multiple fundamental frequency outside as prior knowledge. So from the mixtures, we use an external algorithm which produces the set of fundamental frequency. So here, if we have a mixture of 4 sources, we will have, for each point of time, 4 fundamental frequency estimation. Then we assign this 4 frequency estimation to the different sources, and then this is embedded to the neural network. The neural network will learn the different parameters of the synthesizer, knowing the different model for all the sources. We add the output of the synthesized sources, and this is compared to the incoming mixtures with the same type of spectral loss that is used in DDSP, the differentiable digital signal processing. So it's a multi-resolution spectral loss. So then, as I mentioned, the source models are parametric. It's parametric source models. We have the voice signals, which is an excitation source, which is filtered by a filter, which is an all-pole filter, so only resonances. And to give a little bit more details about the excitation, which is a little bit more complex, because the filter is only, I will give some details also. But then for the source, it's quite a complete source model where it can produce harmonic sounds. So you can see this harmonic part of the signal, of the vocal fold signals on the top. You have all of the top, which produce a purely harmonic spectrum. And then you have a second branch, which produce a purely noise spectrum. But the noise spectrum is also shaped in some way, shaped in energy, of course, but also shaped with a typical noise filter. And also for the, you can see there is also a filter for the harmonic part. And this is also explainable by the production of speech, by the physics, is that in fact we know that the signals produced at the vocal folds has a gradual slope by 6 dB per octave. So all this is embedded in the model. So then, and this produces the spectrum of the excitation source, which is then filtered. So the only, I will say, small change from the pure theory is that noise can be produced at the level of the vocal folds and within the vocal tract. And this is not totally taken into account. We assume that there is only one source of noise for a given sound, either at the vocal folds or somewhere in the vocal tract, but otherwise it really models everything that is in a speech signal. And the filter, I'm going to get back a little bit with the filter. So typically this filter is estimated by linear predictive coding. It's a very easy way to do. So we explain the signal as a linear prediction of a previous samples of the signal. And then we have this filter, which is the second equation on the top. But when we do that, and when we did that, let's say, it's known that this way of obtaining the AI coefficient, the predictive coefficient, may lead to unstable filter. And this was the case in your situation. And so then we had to move to another way to estimate the coefficients, which are known as the LSF, the line spectral frequencies. And one big advantage of that is that regardless of the coefficient you find, you never have unstable filter, because your filter is 1 over AZ. And it's only resonance filter. And if you have unstable filter, you will have resonance which is too strong, and of course it will not work. And basically the spectrum of the frequency response of this filter is a smooth filter with only resonance, which in speech are called formants. But you can also speak about formants for a singing voice. Okay, now we have the full model, and as I mentioned, we optimize, we learn the DNN model using a multiscale spectral loss by comparing the mixtures and the synthesized mixtures from the sum of the synthesized individual sources for which we have obtained the parameters. And the spectral loss comes from this DDSP paper, so it compares Fourier magnitude and log Fourier magnitude at different resolutions. Okay. So for those who would like to have a bit more details about the model, you have here the model. Everything which is blue is input to the model. Everything which is green is what is learned from data. And you can see that everything which is white are what is obtained from the model. So either the parameters of the models or the latent source representation that we have. So we can see here, of course, one of the default or the weakness of the model is that we input fundamental frequency. And so I say that this model is fully unsupervised. It's a bit wrong, because in fact, the F0 extraction model that we have used has been learned in a supervised way. But it can be learned on any type of data, and you can take a pre-learned models, but all the rest is unsupervised. You don't need the separated sources, but in fact, you need to have some good estimation of the fundamental frequency. Another thing also which is that is possible is that you can obtain the separated source by synthesis. as I mentioned in the beginning. This is one of the goals. You can also obtain the source by filtering. So you take the source that you obtain by synthesis, you compute a time frequency mask, and you use this time frequency mask to filter the mixtures, and then you can also, it's another way to obtain the source estimates. Unfortunately, this filtering works better. It's a bit annoying because, in fact, one of the dreams was that the synthesized source will be the best, but maybe the synthesizer that is used here is not sufficiently good to synthesize sources which are sufficiently good. But if we use the synthesized source as an estimation of a softmax to filter the mixtures, then it works sufficiently good. Okay, so what are the results of this approach? First good result. So this is a result. It's metrics typically used in source separation. So I give result for mixture of 4 sources. So then 4 sources means that you have soprano, alto, tenor, and bass, 4 singers, 2 females, 2 male, usually. And you try to separate the individual sources, and you compare the individual sources to the ideal or the target individual sources. And the model that is built in the unsupervised way, because you have prior knowledge coming from production models, it can lead to model that is as efficient as if the model was trained in a fully supervised way. So with the knowledge of having the individual sources. Another findings is that if you take only 3% of the training data, then the models with this prior knowledge with source filter model is as efficient as if you are using the full training data, which is quite interesting, which compares here the full model with the small models. And the third finding is that there is a slight drop of performance when you use only 3% of the data, but this drop of performance is much higher when you use the baseline models with the supervised base model, which was in some sense a little bit overtrained or overtuned to the type of data that it analyzed. Okay, so as I mentioned, there is a drawback of the model is that we assume that the fundamental frequency is pre-given to the model. So the next step that we have worked on is to go towards a fully differentiable model for unsupervised singing voice separation, which means that we do not use at any point of time the knowledge of the source. So basically, we embedded the multi-F0 estimator within the model. So we can then train, and this model is a deep learning model for F0 estimation, and with the expectation that we could train end-to-end the full model, and then have a complete integrated model. So basically, this model starts by computing a time frequency representation, a specific time frequency representation, the HCQT. Then it extracts salience map, which is probabilities, let's say, of having a pitch at this value. So then you have different lines, which give these probabilities of having a pitch at this point of time. And then there is a mechanism to assign this salience to each of the source. And then if you have 4 sources, then you have 4 pitch trace, I would say, for that you can then drive the rest of the model. And of course, this model is a bit more complex to integrate everything because it's not completely differentiable, and you have to do some tricks to be able to transfer the gradient from the output to the input. But basically, this model can become completely differentiable by this trick of copying gradients, and you can go from these signals to assign binary trajectory of fundamental frequency for each of the source. Okay, so this was a little bit of detail about this extension. What's the result of this extension? The first result is a bit disappointing, is in fact this end-to-end approach is less accurate than the baseline semi-integrated approach, whatever we do. And also we had to, that I have not discussed that, but the learning strategy for this model, these fully integrated models, needs to be finely tuned, because if we try to train from scratch, it doesn't work at all. We need to first train part of the models, then freeze part of the models, and then so have this kind of warming up strategy to learn the full model. But the good thing, and which is very nice, is that this model is much more generic and works much better when we have data which are completely different than the training data. So that's and this is also where we see the power of the data to learn from data, the model, and also the power of the signal processing models is still there, because it's what makes the model work for unsupervised setting. Okay, maybe I can do a short demo so you will have an idea of how it works. And okay, maybe I should go there. I have too many mouses. Okay, so there are a bunch of signals, so I'm going just to pick one of the example. So you have example with 2 sources, which work better, of course, and examples with 4 sources. And I would just play the mixture. So the good thing is that if we listen to the resynthesized mixtures, it's quite good. There are artifacts, but it's quite good. And then we can listen to the source that we have obtained. So then this is obtained by Wiener filtering, so by the softmax approach. So let me play the ground truth. So you have seen, so it's not too bad, but you have seen that even in the ground truth, it's not perfect. It's because, in fact, several singers are recorded at the same time. And so then the ground source are not perfect. But again, we don't use at all the ground source for the training. So the fact that the ground source is not perfect is not a problem of the algorithm. So then let me play another example. Okay, so depending on question, I can play other examples, but let me play one example of another supervised algorithm. So this is what we obtain. So it's not too far from the supervised model of baseline, but if you train the model with very small data on the baseline, the degradation appear quite fast. Okay, those some takeaways from this method, that only a small amount of data is needed. Filtering the mixtures is better than synthesis, which I mentioned is not what we expected at the beginning. That we introduce a differentiable, stable all-pole filter for making all this workable within the system with source filter models. And we have a parameterization of the mixtures of the source. Oh yes, this is maybe another example I can play, is that in fact we can change the source, because we have a parametric model. So if we wish, we can change the parameters of the source that we have obtained and then obtain a different mixture. Let me play this example. here is the example mixture again. Oh no, maybe I need to go to the bottom. Okay, we play the original mixtures, the resynthesized mixtures, and the modified mixture. Yeah, there is some capabilities of changing the sound, even if it was a bit extreme, I think, in the change. Okay, so to conclude, I don't know if I had more time or not, but so to conclude, I hope I have shown that it's interesting to go for hybrid deep learning. That the expectation is that you can gain in interpretability, in controllability, and in explainability. In fact, that this hybrid model becomes quite controllable by human understandable parameters, and that it leads also to new audio capabilities with perceptually meaningful sound transformation. Of course, it also has another consequence, is that its frugality, as I mentioned, is that you can expect to have a gain of several order of magnitude. So it was illustrated for this work on unsupervised source separation. And this gain of several order of magnitude can be in the need of data or in the need, or in the need of, in the model complexity. And okay, so this is also, you can say that it's also a way to go towards more resource efficient and sustainable AI, because you don't rely only on data to extract all the knowledge that you need to extract, but you also rely on prior knowledge that you already have, that you know that it's audio that you're going to analyze, and you know how the audio was produced, so you can use this information in conjunction with deep neural networks. And I think I have also illustrated this with one example on unsupervised source separation. Okay, so thank you very much for your attention, and of course, welcome for questions.
Thank you, Gaël, for this great talk. Are there questions from the audience?
Thank you for the talk. I'm wondering, when you've optimized your multi-resolution spectrogram, magnitude spectrogram loss for this source separation, how is the time domain error looking? Is it bad because of completely wrong phase, or it's okay? And if it's okay, can you redistribute the excess signal, like the residual signal between those separated voices to gain extra quality and get rid of the artifacts?
Okay, so I'm not sure I got the point for the second part of the question, but for the first part of the question, in fact, it's one of the magic of this multispectral loss. It's a way to take into account phase. If you have only one scale, one resolution, then you have this scale, this phase problem much stronger, because you only have one scale of the observation of the spectrogram. But by looking at the spectrogram of multiple scales, it's a way of representing phase. And so then there are, of course, problems with phase, but it's not so bad, I would say.
There are questions? Yeah. Yes. That's okay. We'll get to you.
So can this framework be generalized to speech separation too?
So we have not done any experiment on that, but the model is directly applicable to speech in the sense that the source filter model used here, it's a speech prediction model. So then it should work. The difference that I see is that there is one advantage for doing choir singing, which is the fundamental frequency are spread, okay, and you know more or less where they will be. even though that there are some overlap. I mean, like the soprano voice, the range of the F0 for the soprano voice has quite some overlap with the range of soprano of F0 for the alto voice. But in singing voice, you have one drawback, one more difficulty, is that all the voices are very synchronized. And so they are harmonically related, and this is a complexity. Where in speech, the F0 may be closer, maybe not if it's a male and a female, but they are not as synchronized. So which should help the model. And the model does not take into account of any additional noise. But if you try to separate 4 speech voice, I would believe that the model should not be too bad. But we have not tried. And if you want to extrapolate to other type of music, then you will probably need to change the source filter model, the source production model, especially if you want to have piano, for example, or guitar, which do not obey very well to a basic mono harmonic source filter model.
Another very quick question. So the quality actually depends on your F0 extraction network, right? So if your F0 estimation is not accurate, then it's not going to be very good.
Okay, that's again a very good question. So in the paper, there are some analysis, some kind of ablation analysis of the impact of F0 error. And in fact, if you do a 10% error, it's not too dramatic. But then it collapses very fast.
Okay, thanks.
Another question.
Thanks for the talk. I want to elaborate from the first question about the phase alignment and the fact that you said, well, the resynthesis approach is not working so well, but then you use the SI-SDR as a metric, and SI-SDR is very strict about the sample level alignment. So maybe I don't know, maybe it sounds good, but the SI-SDR doesn't look great because the resynthesis doesn't account for sample level alignment also for the loss use, right? It's multi-resolution loss, which should be rough aligned, but maybe it's not sample aligned. I don't know, maybe.
Yeah, I think it's a very good question. In fact, it's exactly the case. I think using the soft mask is producing better SI-SDR because, in fact, SI-SDR is very sensitive to phase problems. And in fact, I have not played sound, but depending on the time, I can play sound. And so you will listen and hear, but you can go to the website also with a bunch of examples. But you can listen to the difference between the synthesized source and the filtered source. In fact, it's true. It's not always less good with the synthesized source, but you hear the default of the model. So you hear that it's synthesized, but of course there are no artifacts. And yes, that's true. I think the phase, contrary to what I did, is not perfectly modeled. The multi-scale spectral loss help to model roughly the phase, but it's not perfectly modeled, and it's why when you want to estimate with the SI-SDR, it works better with mask.
Thanks.
Right. We need to move on to the next speaker, so let's thank Gaël again.
Thank you.